Algebra 2. Today we're going to be doing lesson 9.3, which is about the unit circle, which is very, very, very important to the study of trig functions. So this is just a circle located at the center at the origin, and it's a radius of 1 unit, so 1, which is why we call it the unit circle. So we didn't talk a lot about circles earlier, but here we have a little bit. So from our work with equations of circles, which of the following would represent the equation of the unit circle? Okay, well we can do some elimination. This 1 is not a circle, it's a line, so that can't be right. 2 is a parabola, so that can't be right either. All right, so we have two options left. We have x squared plus y squared equals 1, and we have x minus 1 plus y minus, sorry, x minus 1 quantity squared plus y minus 1 quantity squared equals 1. All right, so both of these have radius 1, but the center of this, which is where both your terms go to 0, here is going to be at 1, comma 1. So this circle is going to look like this. And that's not what we wanted. We wanted something located center at the origin. So the answer to this one is going to be 3, because 3 is centered at the origin, and it has radius 1. The way to tell the radius is going to be this right side squared, when we talked a little bit about completing the square. And the solutions to this are going to be whenever both these terms are equal to 0, which is going to be 1 minus 1 is going to be 0, 1 minus 1 is 0. So we have the center of the second one is going to be up here at 1, 1. Anyway, it's not so important. What's more important is we know the shape and the location of the unit circle, which is going to be this thing given by this equation. And this equation is going to come up for us. All right, so now we want to have some convenient points memorized, or at least known. And we're going to get them by the Pythagorean theorem. And this is going all the way back to geometry. This is nothing but geometry, so dust off that knowledge from your brains and join me at exercise 2. So we consider the right triangle whose hypotenuse, the side opposite the right angle, has length 1, and whose angles are both equal to 45. So this is an isosceles right triangle. So that means that both of our other sides have to be equal, because it's an isosceles right triangle. And we're going to call both the sides x. All right, so, well, it's a right triangle, so we have the Pythagorean theorem. And that means that my hypotenuse, 1 squared, equals the sum of my two shorter sides squared, my two legs, x squared plus x squared. All right, let's combine some like terms and do some squaring. 1 squared is 1. X squared plus that squared is going to be 2x squared. All right, so we're going to divide both sides by 2 and take square root. We wind up with x equals square root of 1/2. We're going back to our radical unit, and we get x equals 1 over the square root of 2. Remember how to simplify radicals. This is equal to square root of 2 over 2. Because if you multiply the top and the bottom by rad 2, with rad 2 on the top, and then rad 2 squared, which is going to be 2 on the bottom. So x equals rad 2 over 2, or square root of 2 over 2. I'm going to say rad because it's easier for me. Yeah. All right, exercise 3, we have another special triangle, 30, 60, 90, which remember is half of an equilateral triangle. So if we imagine drawing the other half, it would look something like that. Okay. I'm just going to erase that for now, because I don't want it to get confusing. All right. So, again, we have the longest side equal to 1. Okay, well, if this is going to be half an equilateral triangle, draw this back, this whole side also has to equal 1. So if this is half of that, this is going to have to be equal to a half. All right, so then we have this just comes from our knowledge about equilateral triangles. And then we're going to have the Pythagorean theorem to find this other side, which we're going to call, I guess, b. So 1 squared equals a, which is 1/2 squared, plus b squared. All right, well, 1 squared is still 1. 1/2 squared is going to be a quarter. And b squared is going to be b squared. So we wind up with 1 equals 1/4 plus b squared. So 3/4 equals b squared. Take the rad of both sides. And we wind up with b equals the square root of 3 over 2. Yeah. Technically speaking, this square root does have a plus or minus solution, but because it's a length, the length of a side can only be positive, so we're only going to worry about the positive one. So even though this equation has two solutions, we're only going to be worried about the one that's positive because it doesn't make sense to talk about something that's negative 3 over 2 units long. This side's going to be rad 3 over 2. Once you're all done, copying this down, understanding this, and judging it back up from the vaults of geometry, join me at the next page. It's our big unit circle. All right. The unit circle is going to be the holy grail of trigonometry because it gives us a lot of very, very convenient values that are going to show up a lot. All right. So we're going to label a bunch of points. All the points here, more or less. Okay, so let's start with the 4 ones that are the easiest, and that are the points that are these points that are on the axes. Because we know the radius is 1, and we know that they're on the axes. So that gives us 4 points for free, which is super nice. Okay, this one's going to have to be 1 over 0 up, 0 over 1 up, minus 1, 0, and 0, minus 1. Those are the ones that we know just by looking at our coordinate plane. But for now, we're going to focus on our first quadrant, where we've drawn 3 triangles that should frankly look quite familiar. All right. So if we look at this triangle that I'm drawing in green right now, this is a 90-degree angle because it's meeting perpendicularly. I'll tell you that. And we know that this measure is 45 degrees. If we're just looking at this triangle, ignoring all the other stuff that I'm drawing over. This also has to be 45. Well, that makes us a 45, 45, 90 triangle. Okay. Well, if you remember what we know about 45, 45, 90 triangles, that tells us that both the side lengths x have to equal rad 2 over 2. So that means that this length is rad 2 over 2. And this length is also rad 2 over 2. Which means that the point that I get to if I go over rad 2 over 2 units and up rad 2 over 2 units is going to be rad 2 over 2, rad 2 over 2. All right. I'm going to erase this because I'm going to have to draw a lot of other stuff here. But just make sure you have the point at the end and you understand where it comes from. And if you want to draw some of these triangles as well, you're welcome to. You may just draw them on another quadrant. Okay. So now let's do one of our 30, 60, 90 triangles. Let's do this one. Okay. Here's 30. So that's the angle we're given. This is again 90, which means that this has to be 60. Okay. Well, if we go back to 30, 60, 90 triangles, we know the hypotenuse is 1. The shorter side is 1/2, and the longer side is rad 3 over 2. Longer leg, sorry. So our shorter side, 1/2. Our longer leg is going to be rad 3 over 2. So if you go back to our x, y, we end up with rad 3 over 2, 1 over 2. And we can do, again, I'm going to erase this triangle so make sure you understand where it all comes from. We can do the same exact thing with this triangle. We just have to switch the sides. So here's our 60-degree angle. Here's our 30-degree angle. 60. So we end up with 1/2. Rad 3 over 2 is now the tall sides have long side. So the point we arrive at the top is going to be 1/2 over rad 3 over 2 up. I'm going to just move my 60 degrees outside of that so it doesn't get confusing. Okay, cool. These are a lot of numbers. We're only a quarter of the way done. But the rest of it's going to be much easier, and I'm also actually going to show you a trick for remembering some of these numbers. So I'm seeing a lot of over 2's, and I'm seeing a lot of square roots. So the pattern I'm going to say is, okay, let's just look at our x coordinates. Good. 1, we're at 3 over 2, we're at 2 over 2. Well, what's the square root of 1? It's 1, right? So this is the same as saying square root of 1 over 2. We're at 3 over 2. Right? Square root of 1 and 1 are the same thing. So if I replace all my 1's with square roots of 1, okay, well the square root of 0 is also 0. And if you divide 0 by 2, you do just get back to the same thing. 0 by 2 is still 0. So this is the same thing as writing square root of 0 over 2. Okay, well, the only thing that's not in this form now is 1. Okay, well, if you can guess, 0, 1, 2, 3. So you got 0s, 1s, 2, 3. Based on that pattern, you should probably be guessing that this is going to be equal to square root of 4 over 2. Square root of 4 is 2, divided by 2 is 1. Okay. So an alternate way to write this, and we see actually the opposite pattern going up the other way. 0, 1, 2. 0, 1, 2, 3. We're going to write this as rad 4 over 2. If that doesn't help you, don't worry about it. You're welcome to just memorize the points. But if it helps you to count up and then counting down with the square roots over 2, that's totally fine. All right. So once you've acquainted yourself with these patterns, by whatever means necessary, we're going to talk about our other 3 quadrants. And we're not going to have to do as much work as we did in the others. We're going to have to draw these triangles again, because it turns out that these are going to have a lot of similarities. Okay, so if we talk about, so we got this point here, right? Let's talk, it's obviously going to be related to this point. Or I'm going to tell you it's related to this point, because if we draw a horizontal line across, we can see that their y-coordinates, they're on the same level. So their y-coordinates are going to be the same. This one's also going to be rad 3 over 2 in the y-coordinate. The x-coordinate, well, all that happened to the x-coordinate is it got flipped across the axis. And when we flip something across the axis, we switch the sign. So we ended with negative 1/2 rad 3 over 2. Turns out the same thing's going to happen to all these points. The y-coordinate is going to be the same. And the x-coordinate is going to switch signs. So with negative rad 2 over 2, rad 2 over 2. Blue is next. We're going to wind up with negative rad 3 over 2, 1 over 2. And we're going to wind up with, and we already did this, like we have 0 is the same as 0, 1 and negative 1. So we're going to build the third quadrant from the second one. All right, so all that changes here is if we're going from this point, go down like that, we wind up all the way down at the bottom. Okay, a little bit bigger than our screen, which is unfortunate, but hey. All right, so we're keeping the x-coordinate the same, and now we're switching the sign on our y-coordinate. So this thing is going to be negative 1/2, negative rad 3 over 2. Right? If we look at our next pair, the green one, then we're going to keep the x-coordinate the same, switch the y-coordinate. We wind up with negative rad 2 over 2, rad 2 over 2. Same thing's going to happen with our blue one. Keep the x, switch the y. And then, because it's a circle, we could either generate this last one from, um, let's just keep going around the circle, just to make a nice picture. But you can also generate it by flipping the y coordinate in quadrant 1. So in quadrant 4, we're going to go across from the red one. And we wind up with, now we're flipping our x back, but we're keeping our y the same. Wind up with 1/2 negative rad 3 over 2. Flip the green back across, so we're flipping the x, keeping the y the same. Wind up with rad 2 over 2, negative rad 2 over 2. Once we flip the blue, we're going to wind up with, I'm just going to do it across. We wind up with rad 3 over 2, negative 1 over negative 1/2. I know this seems like a lot, and it kind of is, but we have a bunch of really good strategies for figuring out how to get these in your head quickly. So we can either do our rad 1 over 2, 2 over 2, 3 over 2, 4 over 2 method to find all the things in the first one, or we can just memorize those points. And then from there, all you ever have to do to memorize to get all the other points is just flip across your axes and reverse your coordinates. So here we flipped, on the red lines, we flipped from here to here to here and back over. So we got 4 points, like that. And then with the same, just connect with the green and the blue. Forgot to do the blue dots. Gotta finish it. All right. All right, so one more thing, and I'm gonna have to erase my beautiful dots because I'm running out of space, and that's life. But we're going to use what we did in the last couple lessons, which we're going to talk about radians. Finish. Polishing this off, and we are all set. Okay. So, if we go back, cast our minds back 2 lessons, maybe 1 lesson. 30 degrees was equal to pi over 6. That's just another way to write the same thing. Okay. Well, based on what we know about fractions, this and 90 degrees can be pi over 2. Spoilers. Okay. Well, pi over 6, we could write this. Pi over 2 is the same thing as 3 pi over 6. Right? Those are equivalent fractions. Okay, so somewhere in between there must be a 2 pi over 6, right? Well, there is. We're going to write the same thing as pi over 3 over here equals 2 pi over 6. So you can see we have these 3 multiples of pi over 6. And if we go around the circle, we find more of them. Everything we're doing in blue is going to be a multiple of pi over 6. And we're going to write them out so that we know. It's important to be able to move fluidly between radians and degrees, because often things will be given in degrees and you're going to have to work with them in terms of radians, just because radians make things easier. Okay, so we got pi over 6, 2 pi over 6, 3 pi over 6. Okay, well, 4 pi over 6, right? What's this next? I'm going to start using green, because it's a little easier to say black. Okay, so 4 pi over 6. Okay, it's the same as 2 pi over 3. 5 pi over 6. Doesn't simplify. 6 pi over 6 definitely does. 6 pi over 6 is just the same as pi. Equals. Okay. 7 pi over 6. Unpleasant, does not simplify. 8 pi over 6 definitely does. 8 pi over 6 is going to be 4/3. 4 pi over 3. Then we have 9 pi over 6, which is of course equal to 3 pi over 2. Then we have 10 pi over 6, which is naturally equal to 5 pi over 3. 11 pi over 6, sensing a pattern here, just not simplify. And 12 pi over 6, this one's a little bit special. 12 pi over 6, which is equal to 2 pi, which is equal to 0. When we're talking about radian measures, in the same way that we say 360 is all the way around, that's the same as not going anywhere, 2 pi is the same as 0. So the angle 2 pi, this thing, is the same as not going anywhere. So we label this point usually as 0 and as 2 pi. Just because it's convenient when we talk about addition and subtraction. If we wind up with a multiple of 2 pi, that's going to be the same as our 0 point. Are we all good with this? All right, then we got to fill in our, we have another kind of line. We didn't color in all the lines yet. I'm going to do this one in, I guess, green. Getting kind of busy, but we can live with it. All right, so we have 0. Again. Then we also have this line. We're up to here. This one. One second, I'll finish drawing these in. And some of these are going to be colored over twice. That's okay. It just means that they're multiples of 2 different things, which happens quite often. Numbers are like that. All right. I'm going to do the numerals in red. Okay. This is equal to, if we go cast our mind back to conversion, this is equal to pi over 4. So in the same way that you read this as 0 pi over 4 or 0 pi over 6, it's the same thing. It's all equal to 0. But pi over 2 is also a multiple of pi over 4. It's going to equal 2 pi over 4, right? It's going to be 3 pi over 4, which is equal to pi over 2. So 3 pi over 4. We're going to have 4 pi over 4, which again simplifies down to pi. 5 pi over 4. 6 pi over 4, which simplifies down to 3 pi over 2. 7 pi over 4. And then we're also going to have 8 pi over 4, which is the same as 6 pi over 12. Sorry, 12 pi over 6, which is the same as 2 pi, which is the same as 0. So we wind up with all these measurements, but if you look at this, you can see there's only actually 2 kinds of angle on the unit circle. You have the multiples of pi over 6, and you have the multiples of pi over 4. And some things, like our 4 axes, are both, and that's okay, even if it's a little bit scary to draw. But that means that if you're able to write something as a multiple of pi over 6 and pi over 4, you're golden. So if you ever have an angle, you always want to try and write it in terms of those 2 things, and we're going to wind up with these super nice points that we spend so much time figuring out how to write and how to memorize. That's all for today. Until next time, make good choices and be kind to each other.